Hi, I'm Paul Bailey, and I'm in the Bardeni lab here at the U. Today, I'm going to talk about two experiments that we use to probe charge and spin transport independently in perovskites. So perovskites are of interest because recently they have shown some photovoltaic applications with high efficiencies, and they also have some interesting spin properties, which make them a potentially useful material for spintronics. And so the first step of that is to see, do charge and spin transport occur by the same physical process in these materials? And so the first experiment I'll talk about uses this tri-layer device on the left here. And so it's comprised of a ferromagnetic layer, which is usually nickel iron, the material that you're interested in studying, in this case a perovskite, and then a platinum layer up top. The nickel iron layer, when it undergoes ferromagnetic resonance, will actually have a precessing magnetization and produce a spin current in our perovskite layer. And so this is spin pumping, and then the spins will travel through our perovskite layer until they hit the platinum layer. And the reason we have platinum is it has high spin orbit coupling. And so there's something called the inverse spin Hall effect, where if you have a material with high spin orbit coupling, the material will actually separate your spins by spin up and spin down. And so the spin current goes through the perovskite, hits the platinum layer, gets separated by spin up and spin down, and we can measure a voltage across the platinum layer. And so this is essentially a spin current detector. And so what we do is we can vary the thickness in the perovskite layer. And so if it's thicker, fewer of the spins will actually reach the platinum layer. We'll get a smaller signal. We can then fit that signal to extract something called the spin coherence length, which tells you what distance spins on average can travel in your material before they're no longer coherent. And we can actually get the spin diffusion coefficient after we get a relaxation time, which would be done with a collaborator or through some other experiment that's still to be decided. But the spin diffusion coefficient essentially tells you how well spins can travel in your material. The next experiment to probe charge transport is called time of flight. And all we do really is have a cathode and an anode on either side of our perovskite. And then we hit one, either the cathode or anode with a pulse laser. And this generates charges at that anode or cathode. And then those charges are going to flow through our material when we apply a potential across it. And we measure the current. And so from this, we're able to see the transit time of the carriers. And so if we increase the potential difference, that's a larger electric field acting on our carriers, and they will have a smaller transit time. It will take them less time to go across our material. And from that, we can extract the mobility. And then the rest of these, this is the temperature here, and the charge of your carriers. We already know, and so we can extract the charge diffusion coefficient. And so if the charge diffusion coefficient and the spin diffusion coefficient differ by maybe orders of magnitude, then that means we can say that the process cannot be the same. So in conclusion, we can make independent measurements of spin and charge transport, and this can actually help us determine whether spin and charge transfer occur through the same physical process. Thank you.